Hi everyone, this is lecture 17, and we continue our study of pairs of random variables. Last class, we learned about the joint CDF for a pair of random variables x and y. Given dummy values, little x and little y, the joint CDF tells us the probability of the joint event that random variable x is less than little x, and random variable y is less than little y. What we found out last class is that using the joint CDF is at best cumbersome and in fact often pretty annoying and difficult to use. For discrete random variables, we found something simpler to work with, and that's the joint PMF. And so for the joint PMF for discrete random variables x and y, given dummy values little x and little y, we have the joint PMF tells us the probability that random variable x takes on the value little x and random variable y takes on the value little y. Using the joint PMF to calculate probabilities of events, however, was pretty simple. For instance, if we have an event B such that x and y belongs to a certain set, for instance, the set B such that x plus y is less than or equal to 3, or for instance, B, the set that x and y belong to a ball of radius 3 around the origin, or you can calculate the probability of B by simply adding up the probabilities of all the points in the set B. And to do that, you just add up all of the PMF points that have non-zero probability that are in the set B. A special case of this theorem gave us the marginal PMFs, Px of x and Py of y, because the joint PMF is a complete probability model from the pair. We can use it to derive a PMF for x or a PMF for y. If we're working with the PMF for x, the way this was derived from the previous theorem was you let B equal the set that x equals little x. Then the PMF of x is equal to the probability x equals x, and that's just the probability of B. And that's just the sum over all x prime and y prime belonging to B of the joint PMF of x and y and x prime and y prime. So there's something funny we had to do here where we had to use dummy variables x prime and y prime. And that's because we're already using little x as a specific value that we're interested in, the random variable x being that little x. However, for this special case, x prime and y prime belongs to B if and only if x prime is equal to x. So the sum then becomes the sum over all y, p of x and y, of x prime equal to x and y. And in fact, I realized I just made a mistake. This should be a y prime. And this is exactly equal to px of x. That is, this sum over y prime is the same as this sum over y because y and y prime are both dummy variables. Flipping the argument around, you can do the same thing to find the PMF of y. So last class we did some examples to show that finding these marginal PMFs is pretty straightforward, particularly when the joint PMF is written as a table. You just do the row sums to find Px of x and the column sums to find Py of y. But this isn't really the subject of today's lecture. It's just part of a review of our previous lecture. The topic of today's lecture is actually the joint probability density function, or joint PDF, which is written lowercase f, subscripts the names of the random variables x and y, and corresponding dummy variables lowercase x and lowercase y. Our motivation for using a density function is just the same as it was for a single random variable x. When x and y are continuous random variables, we know that probability x is a particular value is 0, and probability y is a particular value is 0. And this implies that the joint event that x equals x and y equals y will also have 0 probability. However, what we're interested in is the idea that there's a density such that if you imagine a point little x, here's a point xy, right? And you could be interested in the probability that there's a box of some infinitesimal width dx and some height dy, right? And you'll be interested in the probability that random variable x and random variable y is in that box. And what you'd like when dx and dy are infinitesimal is for that to be equal to the density function times the volume of the box, which is dx dy. This is just the two-dimensional version of a probability density function that we've already seen in one dimension. So this is something of a hand-waving explanation of what a joint density function is, more of a description of a property you'd like to have. The formal definition's on the next slide. Formally, when we have the pair of continuous random variables, we start with a joint CDF. And if you remember, the joint CDF is equal to the probability x is less than equal to x and y is less than equal to y. And it corresponded to saying that if you marked a corner point x and y, it was the probability x and y is in the box. And the way we define the density function is we define the density function of x and y to be a function that if we integrate it over this box, then we recover the probability that the xy pair is in the box. This quantity fxyuv dv du corresponds exactly to being the probability that x is between u and v, u and u plus du, and y is between v and v plus dv. Effectively, what's happening is if we think about a point here, u, v, and this is it's the probability that we're in this little box right here, because this thing has volume unit, du dv. In essence, the density function is just simply a function that is defined as so that we can integrate it and recover the joint CDF. Because of the definition of the joint PDF from the previous slide, In fact, calculus gives us a theorem that says that the joint PDF of x and y is just simply a double partial derivative of the joint CDF with respect to x and with respect to y. This may seem really confusing, but it'll turn out it's really quite convenient because the fact is we very rarely work with the joint CDF. We almost always work with the joint density function, and the joint density function and using it with calculus to calculate probabilities will turn out to be pretty straightforward and kind of nice. Before working with the joint density though, let's go back and revisit this problem we saw last class where we had a joint CDF of random variables x and y, where x was the age of an average first grader, y was the age of an average second grader. We had this incredibly complicated joint CDF to say that x is usually between 5 and 6 and y is between 6 and 7. So here what we'll do is we're going to use our theorem that the joint density function of x and y is the partial fxy x and y partial x partial y. And so what we'll do up here is we'll just make a table uh, of what this two-way partial is. So for instance, on the first row, the partial of 0 is 0, the partial of 0 is 0, and finally on the next row, you get the partial with respect to x, and of x minus 5. So this quantity is going to be 1. And the partial with respect to x of y minus 6 is going to be 0. And the partial with respect to y of x minus 5 is going to be 0. So this is 0. And of course, the partial with respect to 1 is also 0. So in fact, we get a pretty simple answer here. We get that here we have x and y, and the answer is going to be it's equal to 1 for x between 5 and 6, and y between 6 and 7, and 0 otherwise. And my contention is that this is a pretty nice, simple, easy to understand answer. It says that all x's and y's in the box between x's from 5 to 6 and y's from 6 to 7, the density is uniform over that box. This is pretty straightforward and easy to understand. It says uh, a pair of a first grader and a second grader are equally likely kind of to be any age where x is between the first grader is between 5 and 6 and the second grader is between 6 and 7. So my contention is that this joint density function is a lot simpler and easier to make sense of than the joint CDF from which we derived it. So these are just the notes in the book that repeat what I just said. The joint PDF does have some pretty useful properties because it's a density function of probability, right? It inherits these same properties that we saw for one random variable. Specifically, the joint PDF is always greater than or equal to 0, and the integral of the joint PDF over all x and all y always has to integrate to 1. It's the two-dimensional analog of the area under the curve of the PDF being 1. In this case, it's a volume above the xy plane that has to be equal to 1. This theorem is the main reason that the joint PDF is so convenient to use. For instance, if we imagine we have an xy plane, and we ask ourselves, well, what is the probability that of the event that the pair x and y belongs to the set A? Well, the theorem tells us the answer. The answer is that we simply integrate over the region A the joint PDF of x and y. And this gives us the probability because, in fact, this joint PDF times dx dy, you have a little volume unit inside the area A of width dx and height dy, it tells you the probability that the xy pair is in that little volume unit. And all we're really doing is just adding up the probabilities of all the little volume units inside the two-dimensional set A. Okay, so here's an example to exercise our previous theorem. Of a pair of random variables x and y, and the example says that that in fact there's a box from 0 to 5 in the x direction, and from 0 to 3 in the y direction, and that in this box, the joint CDF of x and y is equal to a constant c. And outside of the box, the joint CDF is equal to 0. So the example problem asks us to find this constant c, and also then to find the probability of an event A that x is between 2 and 3, and y is between 1 and 3. So there are a lot of homework problems where the joint PDF has a constant c and you're asked to find it. It's kind of testing that you know how to do a little calculus and you know a fundamental property of the joint PDF that over all x and y it integrates to 1. What this requirement says is that 1 is equal to the integral from minus infinity to infinity over x minus infinity to infinity over y, the joint PDF of x and y, dy dx. We could do the integral the other way, but somehow I seem to like it this way. And this integral becomes the integral 0 to 5 in the x direction, 0 to 3 in the y direction, and over this interval, the PDF is c dy dx. And this becomes two separate integrals, 0 to 5 dx, bring the c out front, 0 to 3 dy, and so this is x from 0 to 5 multiplied by y from 0 to 3, and so this is 5 minus 0, is 3 minus 0. The answer is 15, but I forgot to write the constant c in front. So the answer is 15c. And 15c, we know has to be equal to 1. And this implies that c is equal to 1 over 15. Frankly, all of this calculus wasn't really necessary because when we know that a density is constant over an area, then we know that the integral over that area of the density is going to be equal to c times the area. In this case, it's going to be c times 15, and that is to integrate to 1. The rest of this problem is to find P of A, and this is some pretty straightforward calculus because you're just integrating over the region A the joint PDF of x and y. Right, so this is the integral of x from 2 to 3 and y from 1 to 3, and we put in the value of the joint PDF, 1/15, and then we write dy and dx. And you could work out the calculus, or you could just realize that, oh, this is 1/15 times the area, which is 3 minus 2 times 3 minus 1. And, and so this probability is equal to 2/15. And the point is that what we did is that we had a box here where x goes from 2 to 3 and y goes from 1 to 3. And what we're calculating is the probability that we observe an xy pair in this box. That's exactly what this integral is representing. So this slide is just repeating what I said on the previous slide. So let's end up this lecture by doing the following example. This example turns out to be astonishingly complicated, and it's the final example to show you why joint CDF is so complicated. So here we have a joint uh, PDF, right? And the PDF is pretty simple. The PDF is uniform. It has a value of 2 over this triangular region. So all xy pairs in the triangle region are equally likely. The area of the triangle is a half, so the PDF has to be 2. So the problem asks you to go and from the PDF recover the joint CDF of x and y. Conceptually, this is a simple problem because we have a definition for the joint CDF of x and y. And you just simply integrate over all possible x and y. I'm sorry, with w variables u and v, you integrate up to x and y. And we just integrate the density function. And we'll be careful and use w variables u and v to do this. In one of the revisions of our textbook, I formulated this problem and thought, oh, this will be a simple way to demonstrate how to recover a CDF from a PDF. On the other hand, as I worked on this problem, I spent maybe the better part of a weekend sorting it out, and I got a lot of different answers. And I found I got these different answers because this it turns out to be a super confusing problem. The reason this problem is super confusing is because if we go back to our integral for the CDF, minus infinity to y, the PDF with respect to w variables u and v, what we have here is a situation where the value of this integral depends on these upper limits x and y. And in fact, there are 5 different cases, of which 4 are shown here, that for each of those cases, this integral is something different that you have to do. So the first such case that we're interested in is that x is less than 0 or y is less than 0. So here's an example of that. In that case, the region of integration is shown here, right? And it has no overlap with where the triangular region where the density is non-zero. And so the value of the integral is 0. The next version of the problem we have to consider is where y is less than or equal to x and x is less than or equal to 1. Then the region of integration is showing everything below and to the left of this region. And you can see in the dark region of where it overlaps. I can't draw it here. It overlaps the triangle. And so you have to do an integral over this funny polygon. The third case we arrive is that x is between 0 and y, and x is between 0 and 1. The previous one was y was less than or equal to x. And now we have an integral over that looks like this, and its intersection with the PDF is over this triangle region. And finally, there's a fourth case, and the fourth case involves y is between 0 and 1, but x is greater than 1. And so in this case, we have the following, and we have an integral, which is over part of the triangular region. And finally, there was a fifth case, which I didn't draw, but it's worth mentioning, and that's case E that covers the whole triangle. So, applying the definition of the joint CDF at the top of the page, which looks relatively straightforward calculus. In fact, we have 5 different integrals to do, and each one involves a little bit of work. So we have something very complicated. So I'll skip the next slide that has some of the details and jump to the answers because in fact that's all we really want to look at this point. Okay, so our 5 cases yield 5 different answers ranging from 0 to 2xy minus y squared. There's 2 more cases, and finally, when x is greater than 1 and y is greater than 1, we have the joint CDF is equal to 1. So the 5 cases are all here, and you might wonder, what does this joint CDF actually look like? It's kind of confusing. So here's a plot of the joint CDF in the XY plane. So along here is the x-axis, and this way is the y-axis. And what we see is that as x climbs from 0 to 1, the joint CDF kind of ramps up. But finally, it flattens out and is a big plateau. And kind of the story here is the following, is that if I showed you this joint CDF, you wouldn't really have any idea of what the random variable pair x and y really look like or how they behave. You couldn't tell exactly. But in fact, x and y really have a simple behavior. We know that they have a joint PDF, and it's defined on this triangle. And in fact, it was uniform on this triangle. And that's pretty simple because it says, oh, all points in the triangle are equally likely. It's very easy to understand that. On the other hand, this joint CDF picture, this sort of funny shaped mountain that curves one way and then curves a different way and then has a flat top. It's hard to draw any intuition from that. So this is the final version of the story that the joint CDF is really a pain in the butt, and the joint PDF is the function that's really convenient to use to talk about pairs of random variables, continuous random variables. So here we have another example problem. It's the same PDF that we had before. It's equal to 1/15 for x between 0 and 5 and y between 0 and 3. But the question that's asked is a little bit trickier. It's what is the probability that you observe y greater than x? So doing this requires a little bit more calculus skill, and I encourage you to go offline now and solve this problem. We'll start the next lecture by solving this problem and solving the quiz that follows.